Hello students. So in the previous class we started doing some examples on differentiation of vector functions with respect to a scalar variable. In our case it is t, and we tried to solve some problems based on simple differentiation rule and using some simple vector algebra results. Today I will try to solve one more example, which is somehow a little bit more interesting in a way that it will give you more idea that how to differentiate a vector function, and then we will move to our next topic. So let's state our problem example. I believe it's 4 in this section, but I'm not sure about it, so you may have to follow the whole tutorial. So if R is a vector function, of a scalar variable t, and A is a constant vector, M is a constant, then differentiate the following. So obviously we will differentiate with respect to t. So what are we differentiating basically? So we are differentiating R dot A So of course I wouldn't solve all of these 8 sub problems, but I will consider at least solving 3 of them. So let us start with solution. So let us start with problem A. So the problem A is I'm going to call it as ft. So let us call this function as ft, where ft is equals to rt, because r is a vector function of scalar variable t, dot product with a, where a is a constant vector. So if I am differentiating this function, this is like our whole vector function. So if I am differentiating this vector function with respect to t, so this will be d dt of rt dot a, and this can be written as dr dt dot product with a plus r dot dA dt. Now it is given that a is a constant vector, so obviously its derivative with respect to t would be 0. So this will be 0, all right, and dot product of r with 0 vector would again be a 0 vector, and if we add 0 vector here, then it would remain unchanged. So we can write it as a dot dr dt, and since dot product is commutative, I just exchange a with dot a dr dt dot a with a dot dr dt. So this is the required dot product, or that's the required derivative also of this function r dot a. All right. Now next let me consider problem C. So problem C is, let me call it again as a function f t, which is equals to r t cross product with dr dt. So obviously this is also a function of t. So if I differentiate, then this will be df dt equals to dr dt, or I can write it as d dt of r cross product with dr dt. And now if I differentiate, then this will be dr dt cross product with dr dt and plus r d square r by dt square. Now these two are same vectors. So we know that a cross a, we know that a cross a is a 0 vector. That means cross product of a vector with itself is equals to 0, because they are considered as to be collinear or a parallel. So in a way, if two vectors are parallel, then their cross product is 0. So a cross a it's considered as to be a parallel, and therefore their cross product is 0. So the cross product of first term is 0 and the second term will remain as it is. All right. So this is how we differentiate the term C, or the problem C. Now let's consider problem E. So I'm just skipping one problem mainly because the next problem is simpler in a way. Now R here ft, before I call this function as vector or scalar, let me just write the right hand side. So the right hand side is r square. So let me write it as r square plus 1 by r square, right? So from vector calculus, we know that if r is equals, if we have r as a vector, then r square is basically r dot r, and that's basically mod of r whole square. So instead of writing r square, I can write mod of r square. Now mod of r is a scalar function, so I can simply write as a square as r square. So this mod of r is equals to a scalar r. So remember, this scalar r and this vector r, they are two different things, because this is a scalar function of t, whereas this is a vector function of t. It's just that mod of r, that means the magnitude or absolute value in a way, or magnitude, let's call it, magnitude of r is equals to a scalar r, where a scalar r is also a function of t, but it's no longer a vector. So there is a big difference between a vector r and scalar r, although I am using the same notation. So that means instead of writing r square, I can replace it with scalar r. So let me write it as scalar r square 1 by r square. Now this is a scalar function of t. So instead of writing vector, it's basically a scalar function. So writing ft makes sense. Now I am differentiating with respect to t. So this will be 2r times dr dt, and this one is minus 2 by r cube dr dt. So if I take 2 common, this will be r minus 1 by r cube dr dt. Now this r is basically mod of r. I can write it as mod of r minus 1 by mod of r cube, and then this is basically mod of r dr dt. So this is the required result. All right. Now which problem should we solve? Let me choose so this is simple, this is not complicated. So m is constant, so m will come out of the differentiation, and then this will be 2 dr dt times d square r by dt square. So this is simple. I can consider probably g. So let's solve the problem g. So the problem g is, let me call it as ft first, and then we will see whether it's a scalar function or a vector function. So r square a square. So again we have r square, vector r square. So from the previous problem we can write it as just scalar r square, and this one is vector a square, which we can write it as simply a square, but a is a constant vector. All right. So, this can be written as vector r plus vector a r square plus a square, where r mod of r equals to small r and mod of a is equals to small a. Both are scalar. All right. And since r is a vector, a is a vector, I can now write f t as a vector. All right. Now we can differentiate with respect to t. All right. So, the differentiation with respect to t would go something like this. So, it would not be simple, it will be slightly lengthy to do the calculation. So, let us write r plus a and then r square plus a square, and now here we will apply the product rule. So, the product rule would state that we will have d dt of 1 by r square plus a square r plus a, and we will have 1 by r square plus a square d dt of r plus a. So, now when we differentiate this one, it will be so we will have r plus a, and then it will be minus of 1 by 2 r square plus a square, and then when we differentiate this one, then it will be 2 r dr dt and plus r square plus a square. Then we will have dr vector dt, and the derivative of constant vector would be 0. So, this will be minus of vector r plus vector a divided by r square plus a square, and here we will have times, I can write it as scalar r dr dt of scalar r, and then this one will be 1 by r square a square dr vector dt. So, that means I can take 1 by r square plus a square common, and this one will be minus of r vector r plus vector a dr dt, and this one will be plus vector dr dt. So, there is a big difference between dr dt and the vector dr dt. All right. So, we should not be confused with them. So, this is the required how to say, the result in a way. So, we can leave it up to there. So, it's not a problem. All right. So, now we have this result here. Let me go back to the problems which we had earlier. This one can also be treated in the similar fashion like we treated the problem G. So, you see, just to have a look at these results, and you'll be able to see that in case of vector functions, you first have to make sure that the function is differentiable, and if it is a differentiable function, then all the rules for the differentiation of scalar functions hold true in case of vector functions as well. And all you have to do is to use some basic results from vector algebra and differentiation of scalar functions to prove these results. So, it really didn't involve any kind of complicated calculations. I basically just use some simple how to say results from vector algebra, and I'm hoping that you also be able to solve these problems. So, we will move to our next topic. So, the next topic in agenda is to introduce the concept of vector integration. So, limit. So, first of all, vector function, limit, continuity, differentiability, successive differentiation, dot product rule, cross product rule, addition, subtraction, multiplication by scalar function and all that. So all these properties what we have learned basically for scalar function are holding true for vector functions as well. So we have seen limit, continuity, differentiability of vector functions. Now from scalar function we also have a concept motivated, which is called integration. So integration of scalar function, similarly integration of vector function. So let us define the integration of vector function. Integration of vector function. Integration of a vector function. So let small ft is a vector, and of course if we are doing the definite vector integration in a way, so indefinite vector integration, then the integration of a vector would always result in how to say, a vector function. And if we are doing the definite vector integration, then the integration of a vector function would result into a vector. So it's not like integrating a vector function, definite or indefinite integral would result in a constant scalar or something. So it will always end up being a vector, whether it is a vector function or vector constant vector. That would depend what type of integration are we doing. All right. So let ft and capital Ft be two vector functions, such that ddt of capital Ft is equals to small ft, then capital Ft is called the indefinite integral of small ft with respect to t, and we write integral of vector small ft dt equals to capital Ft plus some constant c, where c is a constant vector. All right. And yes, so this is how we write the vector integration for two vector functions, and you can see that it's pretty much motivated or sort of like a generalization of integration of scalar functions. So there we also had integration of fx dx is equals to some capital Fx plus a constant c. So here c is a constant vector. So let's consider a few examples. And of course, if we have a definite integral, let's say a to b ft dt, then obviously we write integral ft from a to b so equals to capital Ft from a to b. So this will be fb minus fa. All right. So where a lesser equal to t lesser equal to b. So if we are integrating with respect to t between the range a to b, then in that case this will be our required definite integral. So let us solve few examples. So our first example, if ft, the given vector function, equals to t minus t square times I plus 2t cube j minus 3k. So then find first integral ft dt and second integral 1 to 2 ft dt. All right. So let us solve the integral, the definite integral first. So ft dt, now we can write ft as t minus t square plus 2t cube j minus 3k times dt. And when we are doing the integration, so the integral, like the differentiation, like the differentiation where the differentiation went to the each component, in case of integral as well, the integral will go to each component. So the integral will be done on the first component. So t minus t square dt I plus 2t cube dt j minus 3t dt k, and then when we integrate, this will result in as t square by 2 minus t cube by 3 dt, simply I, not dt, so just I, and this one will be 2 by 4 t to the power 4 times j minus 3, so this is 3t k plus a constant vector c. So this is our or I can simplify it a little bit. So t square common, 1 by 2 minus t by 3 times I plus 1 by 2 t to the power 4 j minus 3 t k plus a constant c. So this is the required integral for the given vector function ft, and as you can see, it's basically doing the integration of 3 scalar functions. So you just send your integral to 3 different components, the component of I, j and k, and do the scalar integration. Alright, so this is our required integral, and now we can calculate our definite integral. So 1 to 2 ft dt. So if I calculate 1 to 2 ft dt, then this will be t square 1 by 2 minus t by 3 evaluated at 1 to and 2, then I, then 1 by 2 t to the power 4 t at 1 t at 2 times j minus 3 t evaluated at 1 2 then k, and then c would not appear because then it will be c at 2 minus c at 1. So ultimately value of constant at 2 and value of constant at 1 would again remain constant, and then constant minus constant would be 0. So c would not would no longer appear, and if you solve this whole thing, then you will end up getting minus 5 by 6 I plus 15 by 2 j minus 3 k. So this is the required answer of this integral ft dt between the range 1 to 2. So this is how we solve the problems from integral in the concept of integral calculus, and let us solve one more example. So this one is, so you might be getting the idea that as we did the differentiation of vector function, the differentiation of the integral of vector function is pretty much following the similar rules. It's just that here we are doing the integration. That's it. Nothing special. So let us consider our next problem. So if RT equals to 5t square times I plus tj minus t cube k, then prove that integral from 1 to 2 r cross dr dt or r cross d square r by dt square dt equals to minus 14i plus 75j minus 15k. So the solution would go like this. Here RT equals to 5t square I plus tj minus t cube k. So we have to calculate d square r by dt square. So first we will calculate dr dt. So this will be 10t I plus j minus 3t square k. Then we have to calculate d square r by dt square. So this will be 10 I plus 0, so we will not write that component, minus 60k, right? Okay, and then we will calculate the cross product of r and d square r by dt square. So cross product of r and d square r by dt square. So how do we calculate? So in order to calculate that, we will simply write r d square r by dt square. So our given vector r is 5t square plus tj minus t cube by t cube k times, what did we have, 10i minus 10i minus 6tk, right, minus 60k. So calculating this is this one is not difficult. So I j k, I will write 5t square tj, so t only minus of t cube, this one is 10i minus 10i, and then here it is 0, and then it is minus of 60. So ultimately this, if you simplified this whole thing, then we probably end up getting an expression. So we will probably end up getting an expression something like I times minus of 60 square, so plus 0, that will be 0, plus j times minus of so there is no 10i here, okay. So here we will get so minus of 10 t cube minus plus 30 t cube, and then k times 0 minus 10t. So ultimately we will obtain minus of 6t square, and this will be 20 t cube times j plus minus 10tk. And now we will do the integration. So now we will do the integration from 1 to 2, right? We were asked to evaluate the integral from 1 to 2. So 1 to 2 r cross d square r by dt square dt. So this will be integral from 1 to 2 minus of 6t square I plus 20 t cube j minus 10t k dt. And if we do the integration, then we will ultimately obtain this as minus of 2t cube from 1 to 2 times I plus 5t to the power 4 1 to 2 j minus 5t square 1 to 2 k. All right. So integrating individual components, and now we will substitute the value, evaluate, and then you will probably get 16 and then plus 2. So here we will have 14i, and then this one will be 75j, and this one will be minus 15k. So this is what we needed to prove. So you remember we had to differentiate an expression like that in the differentiation part. So similarly, we had in this problem we have to integrate this r cross d square r by dt square, and this one is a definite integral problem. So we integrated between 1 to 2, and once we got our required integral, we just substituted the value of t at t equals to 2 and t equals to 1, and this is the required answer which we needed to find. So integration of vector function is more or less similar to integration of scalar functions, and like differentiation of vector functions, we follow the similar results of integration of scalar functions for the integration of vector functions. So it's sort of like generalizing the concepts of scalar functions to the vector functions, and we see that all of them holds true in this case. It's just that in case of vector calculus, you are just doing the differentiation or integration component wise. So we are not doing just for one function, we are doing it for the every functions involved in each component basically. I will try to solve maybe one or two more examples based on integration of vector functions, and afterwards we'll move to our next topic, which is basically divergence, gradient and curl. So we'll stop here for today, and I thank you for your attention. I'll see you in the next class.